So thank you for introducing me. So my name is Ashrith, and about 10 minutes ago, someone was asking me, what do you do for H2O? So yes, I'm a security scientist at H2O. I work primarily in detecting anomalies or any kind of bad behavior, malicious behavior, fraud, attacks, and any of those things that come up. But I actually like to call myself a QQ plot maker. How many of you guys know what a QQ plot is? Oh, great. Super. I'm in good company then. So QQ plot, quantile plots, quantile plots, you're just looking at two different distributions, trying to see where the funny behavior is. And that's fundamentally what goes on in detecting anomalies. That's actually good enough if you know how to make QQ plots, but let's go a bit further. Okay, I think suddenly the volume increased, but that's okay. So what I'm going to be talking about today is how do you actually go about designing features when you're looking at malicious behavior. So one of the common things that we do when we're running a machine learning algorithm is we take all the columns that come in your data set and we pray to whatever God we want to pray. And then we say, put it into the model and say, give me the good news. Usually that works, most of the time that works when your data is pretty well done, it's homogeneous and things like that. But a lot of times you actually have to extract information out of the data. And that requires some amount of domain knowledge. And this domain knowledge is not something that is acquired and you can come with it. You can learn it as you're working with the data. Because once you start understanding the interactions, once you start understanding how data, the different columns interact with each other, you can kind of start to build these features. And that's what the primary purpose of feature engineering is. So if you were to look at it purely from a statistical point of view or from a old school modeling point of view, feature engineering is all about breaking down the data into its elements. Breaking it into elements to such an extent that you keep your error to the minimum. And I know I've used something very linear there. I know when we do like tree-based or deep learning, that doesn't necessarily stand, but I'm just using it as a simple example of that. The decomposition part of any data that you're analyzing or any data that you're actually trying to model is time consuming. And sometimes you kind of have to venture into interesting territories that you've not explored before. Usually the case that happens in my line of work. But it does take time, but it's got its rewards. So the general idea always in feature engineering is to try and tease out the kind of information that, that could actually help the model understand what the behavior is. You can almost look at feature engineering as a kind of translation that you provide from the data to the model so that the model better understands what the data is trying to represent or what is the underlying behavior and so on. So as I was saying earlier, one of the things that you need when you're doing feature engineering is some amount of domain knowledge. And the reason why you need some amount of domain knowledge is to create some kind of hypothesis, to create some kind of features. Now, mind you, this is not old school statistical hypothesis where you have to prove something works. It's merely hypothesizing something or theorizing something saying, okay, this kind of a feature can actually work in identifying a behavior. Because one of the advantages of machine learning is you're not using one variable or two variables or three variables to actually identify the underlying behavior. You're using hundreds and thousands of features in an aggregated fashion to identify what the underlying behavior is. So if some of them fail, that's perfectly okay. But that's not your job to start with. That's your job to follow on with. But if you can theorize all these features to a point where you say, these are all something that I think will add value, then you're good to go. So all you have to do is come up with some theory about your underlying data. And what I mean is in the domain, not necessarily how the data interacts with itself. I could have a column which is purely just real numbers and then something which is categorical and you just look at the local interaction. But you should actually be just going just a bit above that, looking at the domain and trying to see how these two interact in terms of what you're trying to model. Then put that into code and then let your model actually tell you what you do. So there are three categories of features that I usually build, and this is something that not sure why that happened. This is something that I have actually, hang on. Is it good? Okay, so this is something that I use all throughout my work. You've got something that's called as global features. something that's called as local features, and a last one, which is a subset features. So subset features are not necessary in all kinds of modeling that you do, but global and local are almost universally required for any kind of modeling that you do. So as we go through, let's kind of try and take a look at what are the different features here. One of the use cases that I'm actually going to bring up is electronic fraud. How many of you guys work in the area of detecting funny behavior or bad behavior in credit card fraud or electronic fraud? Okay, so we have a few hands up there. That's good. What are the usual things you guys see? Anyone want to say what you see? What are the kind of fraud behavior that you guys see? Maybe not? Okay, take it later. So this is a very generic data set. This is not out of any financial organization, so don't worry, I'm not representing anyone's data here. What you see is some form of a unique user ID, the date and the time the transaction actually happened, a related account, what kind of a instrument was used, or what kind of a transaction was done, what kind of a category of transaction was it, the transaction type, the merchant category that you interacted with, the location of the merchant, the source of your merchant, type of operation on the card, and then there are some kinds of subtypes that actually help you classify this much further. Now, if I was new to the field, one of the first things that I would do is I would just take this, put it into a model, and then try to see what comes out of it, and then go from there. Now, but what you need to actually do is start building these different kinds of features. And as I had just explained, stated, one of the first features that you build is this thing called global features. So the idea of a global feature is try to understand what the behavior of the population is. And this is actually very important, because if you look at it, your machine learning model, what it's actually doing is it's just trying to partition two spaces. Let's for all practical purposes, let's assume that this is just a binary space. Fraud, no fraud. What it's trying to do is it's trying to understand what is the general behavior that occurs when there's a fraud, what is the general behavior that occurs when there's no fraud. And what your global features help you establish is a kind of behavior that the general population actually has. In the sense, generally in your population, you don't have fraud. Like if you have a lot of fraud, then I think you might want to fix something else in your financial organization, not your fraud detection system. So what you're trying to identify here is the general pattern about how your transactions are happening, what is the range of transactions, at what rate do you get transactions, what's the period of high transactions, what's the period of low transactions, when is the value high, when is the value low, when is it risky. For example, when you say when is it risky, in the United States, every time you shop at a gas station, those transactions are risky. So when is it risky to have transaction at gas stations? So that's like a very important thing. A global feature establishes your baseline. It kind of helps you establish a baseline behavior. But it also has some pitfalls. It kind of underfits your data. It's generic, global, so it's definitely generic. It's kind of dancing around the mean, or the median. So it has a tendency to underfit the data, not necessarily identify the nuances of your behavior. And if we look at the specific features for the credit card fraud use case itself, you can look at two different categories of global features. One is your seasonality. Time is one of the most important features that you can use for feature engineering. So here you look at the week at which the transaction occurred, the day of the week. Well, Saturdays and Sundays, people are spending big outside. Weekdays, you're not necessarily spending big outside. So that kind of partitions your space right there. And then you're looking at transactional behavior. You're looking at things like, what is the frequency of probability of a dollar figure? That's too big, by the way. I'll try and read it up again. What is the frequency probability of a dollar figure, occurring in your transactions? For example, you tend to see a lot of $10 values, in your transactions, and suddenly you see $100 value transactions. But when you look at the entire volume, there is a higher probability of you risking on your $10 amount than risking on, $100 transaction or $1,000 transaction, because that probably adds up to a lot of it. And that's kind of what you use to create a value probability. So this kind of a feature helps you establish how the general behavior of your credit card user base actually works. And that kind of helps you, figure out what the what your population is. Some of the other global features you can also look at are the number of users, how many number of users are actually there transacting. What is the actual amount of money that's getting transacted in a specific week. Big things in the States, Black Friday, Christmas, Labor Day sometimes, it's kind of new. I think kind of Black Friday is picking up everywhere in the world right now, so maybe it could actually have a global effect. And the mean amount of money you're seeing every week. And then you can also look at the standard deviations. Standard deviations help you establish a region, which kind of tell you, if you step out of this region, it's okay, it's not. But always use standard deviation with caution, because if there is a lot more weight for those kind of features, it kind of stops you from detecting something that's interesting. For me, as someone who detects anomalies all the time, standard deviation is my enemy, but I'm still okay with it, just saying. And then you can look at the ratios, what is the average number of transactions, per given week, what are the categories of transactions that you do. This is, by the way, this is all across your users. This is not specific to any kind of a user. And the next set that you look for is your local features. So local features are the kind of the more interesting features, which tells you, localized behaviors that you kind of want to see. Here, let's say you want to see a category of people. A category, let's take the kind of cards that you have. You have signature cards, you have non-signature cards, two different categories. Partition that space, and then figure out these things. I'm sure the guys who own signature cards kind of, tend to have higher amount of transactions than compared to the other non-signature guys. So, this usually what you do is you pivot it over some kind of a grouping, and these are the kind of features that help you identify local behaviors. So the nuances of a certain data set is what your local features help you identify. And as I said earlier, it kind of identifies the behavior subtleties. It also has a tendency to overfit your data. So this is where I think a lot of you might have kind of had an idea by now. It's kind of a balance between your global and your local, because you want the model to be as generic as possible, but also as local to identify the right kind of behavior as possible. So it's always a balance, but this is how you think about your local features. And if we were to look at some of the examples, you could say the number of transactions or the transaction amounts for the last 7 days per specific user, or per specific user category, or per specific product type for that matter. And you also could look at the total amount of transactions, the mean amount of transactions for every specific user, and the standard amount of transactions to identify the volatility. So the volatility is kind of an interesting feature, which is very specific, but technically, the way I design it, you should put it into like a subset feature. But in this case, I would say it actually helps you identify how volatile a user is in terms of credit card usage. So it would fit more as a local variable, because it can be used all across your users or your user space. Some more local features. So number of transactions for specific days, total number of transactions, mean amount. What is it that you usually daily do? I buy breakfast, lunch, and dinner, $30 every day. On Saturdays, I'm a big spender, $500 every day, every Saturday. So wow, okay, that's a huge difference. So that kind of helps you establish, those kind of numbers as well. And of course, standard deviation. You can also have like the ratios of the total number of transactions for a specific situation. So we have different situations. One of the things that I quote here is we have family emergencies where you withdraw a lot of money in the middle of the night. Kind of skews your numbers. But the model should be able to understand these things as well. Not necessarily, the actual reason for it, but it must be able to understand this behavior at a much more generic level. And that's what your local variable actually helps you identify. And then, you can look at also your ratios. Ratios are kind of a very healthy thing to put into your model. You can look at your transaction volatility specific to a person as well. So That kind of gives you a large idea of how your local variables kind of fit into the model. The subset features are a bit more interesting. Subset kind of comes into picture when you can't necessarily cover a behavior, as a part of the population or as a part of the local, a local variable feature. But they do have a huge amount of influence. Sometimes, generally what you see, stolen credit cards are tested online. One of the ways of testing stolen credit cards online is, I'll go online, on Amazon there are books that they sell for like a cent or a cent or something, and they usually buy those kind of books online because there are hard rules in credit card fraud systems that 1 cent of buying activity doesn't necessarily hit, so they get passed through. So to validate cards, if they're actually working or not, these are the kind of systems that they test. So a lot of credit cards are usually tested online. So you have a very nuanced behavior when you're trying to identify, are these things stolen, are these things or not. So that's where you would have your subset behavior kind of trying to identify. And you could also identify, as I said, it could parallel a local or a global feature. So that's kind of one of the examples I would say when it comes to subset features. So this subset is extremely specific to a domain. Depends on what you're trying to identify, depends on how deep you want to go. But I would still say this is kind of an option, an optional feature set that you would want to include. But the two things that you would want to include are your global and your local, and that should give you a good job. Some of the other things that you can look for in terms of your subset variables, you guys must have seen there are two different kinds of transactions, card present, card not present, and that kind of gives you a valuable insight as well. There are virtual cards, where your credit card is actually represented as another virtual card which you can use it on an online transaction. Stolen cards tend to be used across many different devices. Cards that are not stolen tend to be used across a few or just one device. And sorry, that was supposed to be code. Somehow it came out something wrong. Okay, so then you're looking at the device repetition count, how many times are a certain device is repeated for a certain kind of card. That kind of becomes interesting too in terms of your subset features. So the important checks that you want to do before feature engineering. And this is something that I kind of stress in every talk of mine. Remember, the model is actually not smart. All the model is doing is it's just differentiating between a 1 and a 0, or a yes or a no. The smart is actually between the model and the data, which is you. So whatever you put into the model is the smarts that actually go into the model. So as I was announced, my area is actually cybersecurity, and one of the things that my advisor used to say in the field of cybersecurity is the dumbness is actually between the keyboard and the chair, because that's what the issue with security is. It's the person who actually causes a break of security. So reversal of that, the smartness is actually between the keyboard and the chair in this case, if you want to know. So what you put in is the most important thing. So make sure that what you put in counts, your features and everything. So test your features. How long do they go? Do your features work, when you put your model to production, do they work for 1 day, 15 days, 1 year? And you have to make this decision because it depends on how long you want your model to survive. Do you want to start coding the moment your model, immediately after you deployed your model? Check for correlational features. Kind of subjective, but just make sure you check for correlations in the feature so that you're not putting the same kind of features in again. But look at distributions. Look at distributions across your classes, across how you classify. Look at the confusion matrix, see how they work, and see if you can improve the features. These are some of the interesting things that you want to do as well. So the feature important list. That's actually one of the most interesting things. I actually have a friend who didn't turn up today for the talk. And every time I start a talk about feature engineering, he asks, hey, Ashrith, are the tulips in Amsterdam actually an interesting feature for the fraud detection that you're doing? It's not. But how do you know that? It's a feature importance list, which will tell you, if that is actually important or not. So look at your feature importance list. See how your features are actually listed. And don't worry about your hypothesis. This is not the traditional statistical space. You're looking at the model to tell you what is right or wrong. So in reality, your model will tell you what's right or wrong. And post-analysis, look at your features, look at your confusion matrix, and see what features work for what part of your confusion matrix. That actually gives you one of the most maximum return on investment in terms of the features that you've put in, and then you can go ahead and tune your features much better. Yes, so I think I have 1, 2, 3, how many?
3.
3 minutes, okay, great. Any questions at all?
Yeah. Questions.
Okay. Too many false positives, fraud. Okay, so one of the first question is, banks are overwhelmed by too many false positives for fraud when it's not, while missing false negatives, which are actually fraudulent. How do you address this? So this is a fantastic question, and frankly, it's kind of a difficult one. What you do is the banks have to understand that you have to set a risk threshold. So you will always miss some of the transactions which are classified as false negatives. So a bank must kind of tell you what is their risk appetite. My risk appetite is to miss 0.01% of my transactions as false negatives. And based off that, you kind of tune back. So you use a confusion matrix to kind of tune back and say, if I have 1%, 0.1% or 0.01% as my false negatives, what is the best model I can get? And that's how you always work back and then get the best model possible. There's another one. How do you approach device repetition counts and other feature engineering for IP addresses? So IP addresses is a very interesting space. So what you do with IP addresses is you always try and tie it with devices. So IP addresses associated with devices, and you see what device takes up many different IPs, or what IP takes the same different devices, and you see if those accounts are actually connected to each other. So you have to build a vertical relationship from the device or from the IP address to the account level to be able to classify if a transaction is fraudulent or not. I think I probably have one more. Okay. What is the volume of data, frequency of data, where do you store the data and model? What's the model execution frequency? Okay, that's a big question. Let me try and hit it quickly. So the volume of transactions that I look at are probably, the highest I've looked at is about 22,000 transactions per second. And you can count 22,000 transactions per second across a year, and that's the largest amount of data I've looked at. Frequency of data, well, it's the same number, so you are aggregating that number across how many ever models you're building. And storing the data, I would say the best place to store for you would be Hadoop. I mean, that's the best place. Anyone else has got another suggestion? I'm curious to know. I just use Hadoop. But. And the model execution frequency, well, inline. There is no frequency. The model has to be inline. So that's one of the most important things. For good, what's the standard, what is a standard or a good PRAUC for credit card? Well, I would say it depends on what is your risk appetite again. I wouldn't say you can just put a number to it. I would say depending on the financial institution risk, you will be able to classify this. If yours is a community bank, your risk appetite is probably super low. So you want to be able to flag almost everything that happens. But if you're a large financial organization, you probably have some higher level of risk. So it's kind of a balance between those two. I guess I'm good for now. Thank you. Thanks.